Again, my name is Yan Ding. Uh, uh, right over here is my contact information. Mm, I will use about 40 minutes that kind of to give a presentation. I really welcome your questions, so I can answer anytime. It's about new capabilities and some issue practical applications. New capability here I will emphasize is about cross-shore transport and probabilistic shoreline evolution using wave climate model. Mm, smooth. All right. So I have a little bit outline. Doesn't mean I will cover everything. In an introduction, I will tell this you use a GenCade for project, what kind of issue you may have, or what kind of challenge. Uh, Mostly challenge is to provide a long-term and large-scale shoreline evolution results. And then I will give three cases to describe those challenges. And I will talk about this integrated models, coastal process models for shoreline erosion modeling, such like semis, wave flow. But if you have other multidimensional model can simulate regional wave, current, even sediment, nearshore sediment, you can use that to help set up GenCade and also calibrate the validate the GenCade. I will talk about those details in an example. Here, uh, we I would like to say long term of this shoreline model capability is a kind of order from year to century, multi decades. That would be the best capability. Because even though this is a simple one line model, but it has quite a complicated empirical process modules. So if you consider reliability and accuracy, doesn't mean the longer, more reliable. No, uh, that's just, I would like to say long term means decadal scale in time. And then regional scale, mostly is your project scale. We have a mostly project for coast storm risk management project. Mostly, if you consider Barrow Island coast erosion protection, is about 10 mile, several 10 miles, that kind of scale. Uh, we mentioned before capability of inlet bypassing. We have some empirical to simulate this sediment pathway, but still that is challenging. Challenging is to provide more accurate prediction of long-term morphology change. Mm, that's really difficult. But from the practical simulations, we have some good handle those sediment bypass crossing inlet. And another thing is nowadays we never have problem to only dealing with near natural shoreline or natural coast. From coast to coast for structures and the protection measures and planning. I would like to categorized into structure measure and non-structure measures. We know traditionally we use breakwaters, groins, jetties, and sea walls to limit the change of shoreline and to control, to reduce this longshore sediment transport, so stabilize shoreline variation. Non-structural measure is very popular, used to do this to do beach fill nourishment in rare applications. We may have nourishment before and after storm. So you can call it pre-storm nourishment, post-storm nourishment. Those things significantly change this the natural beach and also stabilize recreational beach. At the same time, you have bypassing and dredging material placement. You may have vegetation impact, dune, and so on. Those the impact of structure, non-structure on the shoreline change, particularly to predict the long-term impact of those measures, is very difficult. One difficulty is we may not have accurate history of those data about the structures, about placement. So sometimes we have a limited transacts of the data based upon engineering the local field study. Now we have more remote sensing data, so we also can using cellular imager to extract the shoreline. We're right now doing those study to implement the like shoreline. I mean, the cellular imager based shoreline model. I said traditional shoreline simulation model, one-line model, is based upon highly empirical non-shore sediment transport driven shoreline changing, based upon principle for mass conservation. But that only longshore transport may not enough to explain the long-term variation of shoreline. So we that's the why motivation we added the cross-shore transport capability based upon we process some models. And but at the same time, we know traditional model has this driven force of financial sediment transport, the Curie wave actions. We know mean current, tidal current, water surface changes, sediment rising, even this dune erosion will change this burn or contribute to the sediment transport system. We have to consider those effects. So good things current GenCade can take in account of current and this zero rising and gravity effect slope. So with those challenges from the practical application and engineering practices, we also try best to provide a capability like Monte Carlo simulation to have some estimation of uncertainties and risks of shoreline change. So with that, I can show this picture based upon current this capabilities of GenCade. If we look at the physical process, we do have empirical models to estimate breaking wave height, shoaling, refraction, diffraction due to structures, and sand bypass and structural probability. And those impact longshore transport. We do have an inlet reservoir model Rusty talked about that. And the inside we can including this practice such like a mining dredging into the model. So you can use that to check this refilling of element, I mean, show bars. And cross-shore here is newly developed. I will show you a little bit detail, but it's included wave and wave current in driving cross-shore transport, and it can estimate the net contribution of cross transport to the shoreline change. We do have a Monte Carlo, so after run Monte Carlo using a wave sample, then you can provide estimation of shoreline changes with a bound of uncertainty. And the structure, I said before, we have a hard structure, including inlet. If you view inlet as a structure, we consider dune, but now the dune we only can consider consistent, no change dune high. Dredging, beach fill, nourishment, and so on. I will go to the second session. It's about practical how to use GenCade or what kind of issue you have for the practical solutions of the protection projects. Mm, the first thing is how to define shoreline positions. I think everybody know that. I would like to emphasize the selection of data is the first issue. Second one, to have a historical shoreline reconstructed from measurement, from serial image, whatever you have, you got to have those shorelines from your data. It it will help you. You need that to do the calibration or validation. We can use mean sea level mostly. We can use mean high water as a data to extract the shoreline position from transect survey data or from satellite imagery. This is an example on around the Absecon Inlet. This is Atlantic City in the Absecon Island and Brigantine Island. Fifth District provides very rich historical data, so we will able to reconstruct data, I mean, shoreline history back to the early 1990s. And this is an equation. I would like to talk about equation because this equation has almost everything how to numerical simulation of this shoreline change. Verb is shoreline position y, and the ds is total closure depth. DC is depth of closure is from Dayton to this the point no sediment exchange. We call that is the depth of closure, and the dB is a burn high, and you can consider burn high change if you have a several rising or several change. Then we have extra source term to consider cross-shore sediment transport contribution to the shoreline change. So it looks like pretty simple, but it behind how to estimate this longshore sediment transport flux Q, how to specify source term of sediment volume, how to calculate the cross-shore transport, and then it's very much varying from case to case. Now, I would talk about this CRC formulation again, because this is an old version, original version of CRC equation. Longshore sediment transport rate determined by breaking wave energy flux. So if you have wave, you can conceptually you can think about like that. Then your longshore transport will generate from left to the right, and control the parameter, empirical parameter called K1 and K2 is fortunately is not a really free parameter. K1 is the dominant parameter, dominate the non-shore by the non-shore flux and the local standard property. One good estimate K1 is around 0.4. If you're familiar with technical report, sometimes mentions 0.39, but I would like to say it's 0.4. So to determine next parameter K2 is somehow it kind of measure of impact due to shoreline curvature, and some anything can cause shoreline curvature, then the K1 turn, this turn related to K1 will play the law. So curvature of shoreline mostly occur if you have a structure or knee side of structure, So a rule of thumb to estimate K2, we have this kind of more than half of K1, less than 1.5 K1. That's good guess. However, you do need to do calibration or validation based upon your historical shorelines. I would like, I mean, that's not enough to emphasize you got to do the validation and calibration. But the validation, I mean, calibration parameter is that much about non-shore sediment transport, but more is about the setup of your structures. I will talk about later. This is a current version. This is exactly current GenCade is using for calculate longshore sediment transport. What I want to say is Magnus and Larsen and Hans Hansen both are the GenCade or Genesis model provided this a new version, but new is because longshore current, mean current effect to the longshore sediment transport included in this calculation of estimation of longshore transport rate. You can say the parameter of this new term, one is about is mean velocity, another is wave bottom arbitrary velocity. Of course, it's using mean current to get the magnitude to estimate the amount of contribution due to current. I have one example to show some case this term is pretty significant. And so I hope you keep in mind in current GenCade no longer the classical CRC is the updated but with wave action only and also current. Another thing is estimation of depth of closure. Of course, if you have measurement data such like a translation cross-shore profile, you can directly using this profile to visually check where is this point with NAS shoreline variation. Then all the material literature provided by CHL can tell you if you can estimate the sigma of variation shoreline position here, and then use that sigma as a criterion to get exactly depth closure. But there is a good literature is one called CHL technical notes. And if you check out this number 4 and 45, you'll get this literature. This literature has a good reference. The kitty using data for wave at all those WES stations. WES is a wave wave information station. It's from west coast to east coast. So, and using an empirical equation of for the depth closure and provide a database mm, about values from different equations. For example, this is a kind of a mean show distribution of DOC along the Gulf Coast. So varying from very short, narrow, I mean, maybe a wave is very small, and a very wide, maybe wave is large, or yeah, beach material is pretty different. So you can use this material as an initial guess to set up your model instead of your wide guess. Mm, Summarizing, you can using Lowell's mean order exchange rate. It's a input data to the GenCade. I would like to talk about this waiver process, how GenCade include diffraction, waiver diffraction around the structure. Because if you don't know the details, you may question the reliability. This model to consider nearshore wave deformation. In fact, we uh, have this implemented using analytical solution of diffraction cross around the half semi-infinity breakwater. So those charges can be, I mean, approximated by this equation developed by Nick Krauss in the early 1980s. And personally, I think of it's a long-term, if the purpose of long-term simulation, this estimation of diffraction coefficient so it's a pretty good. It's good enough. So I don't want to go detail, but I want to let you know diffraction is based upon process. It's sometimes based upon accurate analytical solution of that process, such like this. We have a wave transmission effect in the model. You needed to determine your wave transmit coefficient based upon dimension of your structure, and you needed to determine the how much is a freeboard, and if you our structure is constantly submerged or submerged or emerged both. So if you don't know, even though model provides you three options to estimate the transmission coefficients, you better use an adherence equation to estimate the KT. If you have a morphology behind the structure, I would like to using mesh, observation for shoreline is a calibration, validation material to calibrate this KT, because those three equations are summarized by laboratory wave-form data. I tended to overestimate the KT. That's my experience. All right, this is a practical, using SMS to input data of structure. So you have a location to show you transmission coefficient. You can use the define a predefined coefficient, or you can use in model. But when you use a model, ask you to give a freeboard to your data, not a necessary mean deliver. This is some old manual, probably already changed in the new freeboard to your data, and other parameter, including the slope of a structure. So those details already included in GenCade. Indeed, GenCade is a design tool to help you design structures. And also you can add this beach field and so on. This is tell how GenCade simulate this bypass effect of growing. Um, I don't want to go details, but I want to talk about a practical setup of the reservoir model. You have this conceptual uh, diagram, but if you have real uh, hydrosurvey data, this is a hydrosurvey sometimes 21st and around the Abscon Inlet. Blue is deeper, and then this green is higher bed elevation, and then you for me, I can predefine those inlet morphological elements. I can say this is probably most for the aperture bypass bar, attachment bar, and the other side I can also have attachment bar, even though it's not very obviously, but I know something existing, and then we can definitely have a channel, but this aperture scale is so big. Flood show is way behind, including this backway. So when we define the parameters of volumes, you can say from the menu, you have an initial volume, you have equilibrium values. So you can punch a number over there. But at the same time, you can input your judging event data. If you have some practical operation happened somewhere, you can put the volume if you know. Then those events will be included in the calculation of bypassing. Uh, I have this validated model for simulate shoreline evolution across Abscon Inlet. This is a pretty uh, classic case. It's include a structure and a beach fill. This is a time series of shorelines at this location, this transact. You can say black line is a simulation, symbols are from the observation transact data. And so most jumps, I put the arrows, is indicates one beach fail event based upon historical data of beach widening. So you can edit that and have your calibration period over 80 year and another 80 year for validation. We don't have that kind of very straight the validation, because during the validation, structures still keep changing. So you still need to tune the parameter about the structure during the validation, but only you can keep mostly is calibrated K1 and validated depth of closure, those parameters. So looks like pretty good validation, calibration, the validation results. The GenCade can capture shoreline long-term trend. For example, from 2004 to 2011, there's a beach fill or nourishment during this 7 years. You can say the shoreline retreated constantly. And so this is why this area called the erosion hotspot. And then if you have beach fill, then beach fill tend to maintain, hold the position. However, during those high energy time, sudden erosion, due to storms, you can find from the measurement data, also model results also reproduce those signals in the results. And So with that, you also can double check your shoreline position by putting those on Google Earth. For example, 2006 summer, 2000 May 2008, August 2011, October 2014, May 2015 till November 16. So you can see the change. Sometimes you can find the picture of cellular imager just captured right after this beach fell, and your simulation indeed included you felt safe for your prediction and validated model. And the extremely situation, no beach fell and quite a lot of erosion force, and you can say simulate the shoreline. This shoreline data is mean high water, match the this large scale shoreline variation, and also very much show the curvature between the two structures. Those good things is about we have a long-term capability, regional capability, but we also can tell you how much accuracy we can have. You can use Pearson correlation coefficient and the root mean square measured in feet and the relative root mean square and in relative to the maximum beach change to quantify the errors of the model. So back to the bypassing effect, the inlet result model can provide this bypass flux. Branching flux means transport from south to the north to the Breaking Island, and the blue is transport from north to south. Of course, this size dominate downdraft direction is from south to from north to south. Sorry. You can calculate the bypassing effect with using bypassing factor, but never mind. But more important is how could be this predicted volume change. A good things historically we have pretty good data. Those symbols are show volumes, and they also provide dredging volumes. So simulated red line pretty much went through all those measured volumes, and also because dredging events input parameter definitely have a jump, it's actual jump. And you can use this validated model to do this feasibility study of a design. This is a typical wild picture. What if we use a growing group to protect the shoreline? Then you first define where is the limit. This is a dune toe, and this is after 3 years without a project shoreline position, and the blue is with a structure shoreline position, and the white line is a design template of a burn. That means this is from the template. So you can use those criteria to check your model performance and then compare shoreline change among your alternatives. And you can go to Google Earth to check details. If you're familiar with Atlantic City, this is boardwalk right over here. And those dark in color show as dune. This is dune. One more thing is we know shoreline change by the GenCade control mostly by longshore sediment transport. So if you have a structure and then like breakwater plays a lot in reducing the wave energy and reducing transport. So if look at this layout of structure in the same as the two-dimensional model, the results is simulate the longshore current uh, by the same as what I want to say is red line is estimated the longshore sediment transport flux every year, 3-year average. And the blue is average without the project. So you can say if under protection of structure, the longshore sediment transport very stable, very low. However, after this last structure, then sediment transport rate will be recovered naturally to the natural transport the magnitude. So this transition period, sediment transport very much active, so-called downdraft erosion. This is a side effect of a structure. This kind of phenomena or this kind of estimation from the longshore sediment transport point of view also can be proved by the same as two-dimensional morphology models.